So I've started to record. So if you drop out, if you suddenly can't see it or whatever, don't worry, because it will be recorded and you will be able to see it later. So today, electrochemistry 2. It will be helpful if you have some paper and something to write with so you can have a go at some of the questions. I'm going to leave quite a lot of them. I'm not going to go through all of them because next week I will not be here. I have to be away. And I'm going to send the PowerPoint to your teachers so you can have a go at all of the examples then. But we're going to do some of the examples, so hopefully you feel confident. So are we ready? Yes, we're ready. Okay, let's go to electrochemistry 3. Okay. So this is about practicing what we did in the last 2 sessions, but particularly last time. So we're going to straight away start with writing some equations. And I want to remind you how it goes and then give you some to do. So the thing to remember is that when we have a positive charge on an ion, we have to add an electron or two to it, and then it becomes what we call discharged or not charged. Okay, so this is what happens in electrolysis. Very simple. You just have to match the number of positive charges to the number of electrons. So straight away, let's have a go at just writing it for these other ones here. So we've got Cu1 plus, that's copper 1, K plus, Al3 plus, and the copper 2 ion. So just have a go. If you don't have paper, pen, don't worry, just do it in your head because it won't be difficult. It really isn't difficult, but just have a go now to make sure you can do that. They're easy. I just want you to, sometimes just writing equations is very good practice for an examination. Just spend a minute or two doing it, and then we will move on. I'm sure most of you find no problem. Usharika, no, they find it really easy. Silver Spring are finding it easy. I know they are. Excuse me. So just remember that each electron has one negative charge, you know that, and therefore you need just the right number to get rid of the charge. I'm sure everybody can do this. I'll show you in just a moment. Hello, Dandora girls. Oops, you've gone. Kabiro, get it a little bit closer to the camera, please, and I will see. Correct. Correct. Good. Well done, Dandora and Kabiro. Well done. Very good. So we don't want to waste much time doing this because we're going to move on to other things, but I'll just remind people, I'll just do the one for aluminium down here. Aluminium is 3 plus, and so it needs electrons, but it will need 3 electrons to turn it into Al. Okay, so you just match the number of positive charges to the number of electrons. There is only one which I haven't mentioned here, and I should have, which is H plus. And H plus, obviously, if I add one electron, will make H. But that isn't good enough because hydrogen exists as a diatomic molecule, two atoms joined together. So if I have two H's here, then I will need two H's here, and those two H's will need two electrons to be taken from them. So this is the one example in the cations. Do you remember we've said we would write cation like this, like that is a positive charge. In all of the cations, only hydrogen has to be doubled like this. Okay? All right, let's move on. So this is the anions, the negative electrons, and they lose an electron. Now, there are two different ways of writing this. You can either lose an electron, actually take it away and turn it into chlorine. But again, chlorine exists as diatomic molecules, so I will need 2 Cl minus, and that means minus 2 electrons. Or I can write 2 Cl minus turns into Cl2 and 2 electrons. It means the same thing. Okay, it means exactly the same thing. So just have a go with the others here. Don't do the one at the bottom, the OH minus. I will show you the OH minus one, unless somebody is very clever. We did it last time, but I don't expect you to remember. Have a go at the bromide and the oxide ions. Remember that bromine and oxygen go around in pairs. In other words, bromine atoms exist as Br2 in the molecule and oxygen as O2. We know that. Just make sure you can do at least one, because these are important. If somebody wants to show me their answer, that would be great. Your Dandura, it's very good, but it's not balanced. You're right that it forms Br2 and O2, but that would mean that you would need two Br minuses to make a Br2, wouldn't you? Look at what I did there. Silver Spring, have you got some ideas? Can you show me your answers? Kabiro, let's have a look. Little bit closer, please. Nearly, but yes, that's right so far. But don't forget that you need the oxygen and the bromine to end up in pairs, okay? They have to be in pairs. Whoops, sorry, Dandura, you've disappeared again. Right. Nearly, but then, oh, the bromine is completely correct, but the oxygen isn't quite. Let me just show everybody. So with the bromide here, it's going to lose, whoops, sorry. What's happening with my pen? It's going to lose an electron and it's going to turn into Br atoms. But the Br atoms join together to make Br2. This is not balanced. Let me show you it in pictures. So if I have a Br minus and it forms a Br and a minus, but this actually exists as Br2, then I would need 2 Br minuses to make the Br2, and I would get 2 electrons. In other words, it would be 2 Br minuses lose 2 electrons to turn into Br2. Okay? Because it goes around as Br2, I have to count that in my equation. Okay, that's really important. Let me just get rid of all the rubbish here. So I'll write the equation. So at the moment, my equation is incorrect. So here I am. I need my Br2 here. So I need 2 Br minuses, and therefore I'm going to lose 2 electrons. Now, oxygen would have to lose 2 electrons to form an oxygen atom, but it exists as O2, so we need 2 of these, and therefore it's not 2, but 4 here. Do you see that? 2 oxygen, so here's an oxygen with 2 minuses, and I need it to make an oxygen attached to an oxygen. Well, then I would need 2 O2 minuses, and I would produce 1, 2, 3, 4, 1, 2, 3, 4 electrons. So that would be 2 O2 minus turns into O2 and 4 electrons. Okay? So these are quite important. Now I'll give you the last one in just a moment. Let me just erase all this because we don't want it. Okay. The last one you are not expected to remember. It is 4 OH minus 4 electrons turns into 2 H2O and oxygen. You are not expected to remember it. It is crucial that you remember that oxygen comes from OH minus, but don't worry about remembering it. Now, going back a slide, I want you to remember the oil rig or Leo goes girl, when the sodium here or the copper or whatever is gaining electrons, and gaining electrons is reduction. Gain electron equals reduction. Okay, and over here, these guys are losing electrons, and that's oxidation. Losing electrons is oxidation. Okay, so try and remember that. Now, next slide. In aqueous solutions, and it becomes a little bit more complicated, we have water present, and water splits into H plus and OH minus. Because it does, we can get other products. Now, what we said last time was this, and I will show you an example of this in just a moment. If the cation, that's the metal, if I have an electrolysis, let's say, of copper sulfate, if the metal is less reactive than hydrogen, then the metal will be produced. So copper is less reactive than hydrogen, so copper will be produced. And if the anion is chloride, then you'll get chlorine, but otherwise it will be oxygen. So let's look at predicting. So here are some electrolytes, and I will show you how it works, okay? This is quite important because quite often you have to do this prediction of what will be formed. So let's have a look. So in molten, these are all liquid here. There's some more down here. When they are liquid, the only ions which are present are the ones in the chemical, so Na plus and Cl minus. In K2O, there is only K plus and O2 minus. There are two K pluses, but that doesn't matter. In CuBr2, there will be only Cu2 plus and Br minus. And in AgCl, there will only be Ag plus and Cl minus. Now, the positive ions, the cations, go to the cathode. So at the cathode, the only thing that can be produced here is sodium. In the second one, the only thing that can be produced is potassium. The third one, the only thing that can be produced is copper. And in the last one, it must be silver. Can you mute, please? Thank you very much. Thank you. Oh, sorry, I didn't put a minus on there. In the sodium chloride, at the anode, the only anion is chloride, so the only thing we can get is chlorine. This can only be oxygen. This can only be bromine. And once again, this can only be chlorine. There is nothing else that can be formed. So just have a go at the last two. Just see if you can explain, see if you can tell me what ions are present and what will be produced at the cathode and the anode. Asharika, have a go. Come on, have a go. Don't unfocus. Yes, I know you're showing off to your friends, but let's have you trying to concentrate here. Glory, see if you can predict what would be formed from MgI2 and ZnCl2. Just list the ions and see the only thing that can be produced. The positive goes to the negative. The negative goes to the positive. Just have a look at the ones which I did and see if you can understand. You can do it, Kabiro. Yes, you can. St. Michael's, I know you can do it. Come on, Glory. Come on, St. Mary's. This is easy. These are worth being able to do because this is very, very common examination question. Very good, Asharika. Who's that? What's your name, please, Asharika? I know you don't want to show off, but it's, oh gosh. Bit closer, please, Dandora. Alifia. Wait, that's a really unusual name. I really like that. Sorry, I've embarrassed you. That is absolutely correct, Dandora. Very good. Very good. So everybody else, the people who have shown the answers so far have been correct. And what they have done is they have said, okay, in magnesium iodide, the only ions are magnesium, which is always 2+, and iodide, which is I-. In zinc, it must be, in the zinc, it must be Zn2+ and Cl-. Ooh, lost that. So at the cathode, which is negative, the magnesium will be formed. And at the anode, it will be iodine. And in the second one, it will be zinc and chlorine. Now, it gets a bit more complicated when we have aqueous solutions. So I'm going to show you how this works with aqueous solutions. So we've still got the Na plus and the Cl minus, obviously, and the copper and the chloride and the copper and the sulfate. Do you see what I'm doing? I'm just splitting them up, and hydrogen and sulfate. Okay, that's not complicated. But added to that, there is also always, when it is AQ, H plus and OH minus. Now the H plus forms hydrogen. The OH minus, as we just saw, produces oxygen. Now the cations is easy. Because although I haven't listed all the metals here, the most reactive are at the top and the least reactive are at the bottom. And what it says is when you look at any pair of them, so Na and H, the less reactive one will be produced. So it's this one. So at the cathode, I get hydrogen. Okay. In the second one, I have copper and hydrogen. Well, copper is below hydrogen. So in the second one, copper will be produced. So copper here. In the next one, it's copper and hydrogen. So copper. In the last one, there are two hydrogens, so it has to be hydrogen. Now, at the anode, the rule is if there is chloride, it will form chlorine. So there we are. So that forms chlorine. There's chloride. It forms chlorine. Ah, there's no chlorine here, so it produces oxygen. There's no chlorine here, so it produces oxygen. Now, so it may seem a bit strange that, for instance, copper sulfate will produce copper and oxygen, but that's what happens. So what I'd like you to do now is to have a go at the last two. Here they are, magnesium sulfate and zinc chloride. See if you can work out what the ions are and what is actually produced. See if you can work that out. Work out the ions which are present first, and then see if you can work out what will be produced at the two electrodes. Come on, Gloria, you can do this. Come on, Sir Michaels. Come on, Kabiro. Come on, Sir Marys. Dandora. So magnesium sulfate, what ions will you have present? Well, you'll have magnesium and sulfate, but it is AQ. So you must also have hydrogen and hydroxide from the water. So what's produced? Well, it depends on the reactivity for the cation. Wow, great answer. Really, really good. Really good, both of you. The stars from Usharika and Dandora are getting the gold medal at the moment. Yeah, we're that good. Those people who've got it right already, why don't you show one of your friends how to do it? So that we can move on, because time goes on. That's very, very good of the two of you to help other people. I really like that. That's excellent. Gloria, I haven't seen an answer yet. Come on, Gloria, let's see an answer. St. Michael's, let's see an answer. Have a go. Come on. You can do it. I know you can do it. I do know you can do it. Come on, get the brain working. Come on, Kabiro, let's see an answer. I'll help you just a little bit. I'll help you just a little bit. Okay. So in magnesium sulfate, we will have magnesium ions and sulfate ions, obviously. But because it is AQ, we will also have hydrogen ions and hydroxide ions. Now, for these two, we have to go to the reactivity series over here and find out which is more reactive, magnesium or hydrogen. Not quite, St. Mary's. You're not following the rules which we've got. Nearly, but you've got the right ions, but don't forget that with water, you've always got, like I'm showing here, have a look at my screen. You've got H plus and OH minus. And with zinc chloride, I'll have zinc ions, whoops, and chloride ions, and hydroxide ions, and hydrogen ions. And then it's a competition. So let me show you with this one with the with magnesium. Let me just get rid of all the stuff which is in the way. Be done in just a moment. Okay, we'll just look at this one. Okay. Oops. Okay. So here we go. For those people who are not sure, this is the last one we're going to do. No, that's wrong. Okay. So I've got magnesium sulfate. So I've got magnesium and sulfate, obviously. But when it's AQ, I also have H plus and OH minus. Mute, please. Now, I then look at the cation. I look, is it magnesium or is it hydrogen produced? It will be one or the other. So I find them in the reactivity series. Hydrogen is here and magnesium is up here. The least reactive one is the one which is produced. So it will be hydrogen. So at the cathode, I'll get hydrogen. At the anode, the question is there Cl minus? If there is no Cl minus, then I will get oxygen. And because it's sulfate, don't worry, it's the OH minus. The OH minus makes the oxygen. The H plus makes the hydrogen. So zinc chloride will be Zn2 plus and the H plus, and Cl minus and OH minus. So comparing these two, zinc is higher, here it is up here. So it won't be that, it will be hydrogen. Over here, is there chloride? Ah, yes, there is chloride, and therefore we will get chlorine. Now, for those of you who don't really get it yet, if you look back at the recording and have another go at this sometime, it will make a lot more sense, I hope. But we're going to move on now. You can see this later, okay? So part 2 was Faraday's law. And I'm just going to I'm going to show you 2 examples. Faraday's law was all about how much of a chemical we get. Don't worry, we're only going to do about another, well, less than 10 minutes on this, and then we will do something a bit more interesting. More electricity means more product. And it was important to know that 1 mole of electrons is called a Faraday, and is 96,500 coulombs. Okay, a coulomb is an amp time a second. So what we did here was we said, how many Faradays are needed to produce a mole of Na? Well, to do that, all we have to do is we have to write an equation. Na, well, that comes from a mole of 1 mole of Na plus adds to 1 mole. Remember, mole is just a number like 5 or 20. It's a big number. So to produce 1 mole of sodium, which is 23 grams, I need 1 mole of electrons, and that is 1 Faraday, which is 96,500 coulombs. Okay? So if I wanted to produce 2 moles of Na, I would, yes, you can. I would then need 2 moles of electrons. Okay, if I wanted 2 moles of Na, instead of 1 here, I would want 2. So I would need 2 here. Chlorine is a bit different because chlorine comes from chloride, losing an electron to form chlorine. But it's Cl2, 2 Cl minus, 2 electrons. Now, it doesn't matter whether they are gaining electrons or losing electrons. To produce 1 mole of chlorine, I need 2 moles of electrons, and that's 2 Faradays, which is 2 times 96,500, which will be 193,000 coulombs. Okay? So that's quite important that we're able to work out just the equation and then how many Faradays, how many moles of electrons. Okay. So how about these? Just have a moment looking at these. So this one is Cu2 plus 2 electrons goes to Cu. This one is Mg2 plus 2 electrons goes to Mg. This is Al3 plus 3 electrons goes to Al. But 2 moles of Cu, 1 mole of Mg, 2 moles of Al. How many electrons would we need for 2 moles of Al? Everybody have a go. Everybody have a go just now. You don't need a calculator for this, Sharika. You really don't. Are you checking that 96,500? Not how many coulombs, how many Faradays? Are you okay, Kubiro? Cool, excellent. Dandura girls, their heads are going to explode because they're putting their jumpers on their heads, their sweater on their head. Maybe the head is too cold, but oh no, it's okay. Oh, it's okay. I thought maybe she was dying of cold. I hear it's only very cold today in Kenya. Well, yeah, 3 Faradays for 1 mole of aluminium, but how many for 2 moles of aluminium? Come on, Glory, concentrate. Let's see if somebody can get the answer and get it out quickly. Dandora, closer, please. 6F. Correct. Very good. Correct. So let's just look at this. So in the first one, 1 mole of Cu needs, it says here, 2 Fe, so 2 Faradays. So 2 moles of Cu would need 4 Faradays. 1 mole Mg needs 2 Faradays. Oh, there we are. Now, 1 mole Al needs 3 Faradays. So 2 moles of Al needs 6 Faradays. 6 times 96,500. Now, let's have a look at a question, because this is where it gets used. Sorry, a mole of oxygen. Because oxygen, O2 minus electrons goes to oxygen in pairs. So it's 2 there, 4 electrons. So 1 mole O2 needs 4 Faradays. Okay? All right, so let's move on. So here's a question. This is a proper KCSE question. What mass of Na will be produced if 20 amps is passed through molten NaCl for 40 minutes? Molten NaCl, so only Na and Cl can be produced, sodium and chlorine. So we work out the coulombs, amps times seconds. And last time we did some examples. Here's some examples. These were the examples. And you just had to work out amps times seconds. So here are the answers. I'll give you them now, but you can have a go later. 20 times 2 times 60. Oh, what's that? 40. Oh, 40 minutes. Sorry, I've got I wrote down the old calculation. This one is correct. This one is correct. This one is incorrect. Okay, this one here is correct. And this one is correct. 10,000 times 3 for the hours to turn it into minutes times second times 60 and times 60 to turn it into seconds. There we are. So here's our question. What mass of Na, 20 amps, 40 minutes? Okay. Well, we work out the coulombs first. So we say, okay, that's 20 times 40 minutes times 60 seconds, which is 48,000 coulombs. So the first thing we always do is to work out the coulombs. Then we say, what does the sodium need in this case? There's the equation, Na plus 1 electron. So in other words, 1 mole of Na will require 1 mole of electrons, 1 Faraday. So how many Faradays have we got? Well, we just divide the number of coulombs we have by 96,500. Well, that's about a half a Faraday. Well, if I've got half a Faraday, I can get half a mole of sodium. And a mole of sodium weighs 23 grams. So it's half times 23, which is 11.5. You will get this question sent to your teachers so you can have a go at it again. You can see it again. Here's another one. This is the mass of copper from Cu2+. How much will be produced if 4 amps is passed for 13 minutes? I'll tell you what the answer is there. And when your teachers get this calculation, it shows them all the working. Okay, it's all there. But the answer is just about 1 gram. So if you want to do it yourself, if you get the answer about 1 gram, you're correct. Okay? But now we're going to move on. So I'm going to stop sharing that. I hope you feel a bit better. Do you feel a bit better about electrolysis? About the same or worse? Usharika feel a bit better. Kabira are not sure. Glory, do you feel a bit better? About the same. Thank you, Silver Spring. Very good to see you. Thank you very much indeed. St. Michael's, Better. St. Mary's. St. Mary's? Bit better. Okay, that's good. St. Michael's? Any better? The same or worse? A bit better. Okay, good. Have a look at it again later if you want to. You can see it easily. But now I'm going to go on to something completely different because two of the centers have asked to do rates of reaction. Rates of reaction is quite nice, and it's quite fun, really. So I'm going to do it now. So here we go. Rates. Excuse me. Okay, this is rates of reaction number 1. Whoops. Let me share again. Here we go. Rates. Okay, this is called rates of reaction 1 and 2 because it's got the first bit is me explaining some things, and then there are some questions which you can do next week when I'm not here. Okay, so here we go. Okay. Here's the syllabus. Don't write it down, but it tells you some things, some terms which you need to know. Collision theory, activation energy, the effect of concentration, pressure, temperature, surface area, light, catalysts. And then you have to know about certain experiments, calcium carbonate with dilute acid, sodium thiosulfate with dilute acid, a metal with an acid, and hydrogen peroxide with catalysts. Okay, so what I'm going to do is I'm going to try to show you some of those. It then goes on to reversible reactions, but we're not going to look at those. I'm going to show you part of a little film by an American teacher. She's very loud. I'm going to show you part of it, starting round about.
First assumption of collision theory. The first assumption of.
Okay, she's going to tell you about collision theory. Collision theory happened in about 1905, so a very long time ago, and it had 3 very simple ideas. That to react, and people didn't know this to start with, the particles must collide with each other. Second, they must be in the right orientation. In other words, they must crash into each other in a particular direction. And third, and most important, they must have quite a lot of energy. So here we go. Let's listen to her explaining it.
Of collision theory is that the particles must collide with one another in order to react. Most particles will act like billiard balls in a game of pool, and when they collide, they bounce off each other. The collision itself.
I can't deal with her accent. So it's like particles colliding with each other. But it's also true that they must have enough energy. You have probably seen this sort of graph before. It's called an energy profile diagram. The reactants have to get up to a particular energy before they can come down the other side and turn into the products. But first they have to need to get up to the top. If they don't get up to the top, they can't slide down the other side. It's like getting a bicycle and riding over a hill. If you haven't got the energy to get to the top, you can't enjoy sliding down the other side. The little bit in between those, between the reactants and the products, is called the activation energy. The activation energy can be quite high or can be quite low, but that's what it's all about. That's what activation energy is. Now, when particles collide with each other, quite a lot of the time, we heat them up. And we heat them up because it makes them go faster. And in making them going up faster, it supplies them with enough energy for them to go quickly and therefore crash into each other. But there's one other thing. This is meant to be ozone and nitrogen monoxide. And when they crash into each other, sometimes nothing happens. But sometimes they collide, and they have to collide properly. So when they collide properly, the N was hitting one of the O's, and therefore the reaction happens, but otherwise nothing happens. So they have to collide with each other properly. So collision theory says that the particles must collide, they must have enough energy, and they must have the correct orientation. Those three things are very important. They must be able to crash into each other. They must do it with enough energy, that's enough force, and they must be in the right orientation. Now, you almost never have to remember the orientation. Almost never have to remember that, okay? I would like you to remember collide, energy, and orientation, but you will almost never have a question about the orientation. Okay, so let's move on to the next question. So I've got a couple of experiments here which will show you a bit about reactions. Sadly, I can't be there in a laboratory with you, but this first one shows a gas being evolved. It's calcium carbonate, and what is important is noting it slowing down. So let's have a look. So this is me. This is calcium carbonate here in a little dish. This is hydrochloric acid here. And this is a conical flask, and the gas will go up here and into this, which is called a gas syringe. So what you will see is the plunger comes out and the volume increases. Okay, so here we go. So add the powder, put the top back on really quickly, and you can see the gas coming out really fast. Now, it's quite difficult to see, but I'll go on just a little bit more. That's about 5 seconds, and it's produced just over 60 cubic centimeters. Now we'll move on. And if I stop it at about 10 seconds, whoops, sorry, I didn't mean to stop it there. Sorry, I got it to restart again. What you can see is it's going to 60, and now it's slowing down. 70, less and less gas is coming out. Now, that is really important. That is a feature of all reactions, that they slow down. So although it only took about 5 seconds to produce 60, after half a minute, it has only produced just over 80. In fact, it looks like it's just about stopped. Okay? All right. Now, that is important because of something that it means. So what it means is this. If I draw a graph, can I draw a graph? Let's hope I can draw a graph here. Ah, yes. If I show you a graph, and this is concentration up the side, and then this is not a very good color, is it? I'll just change to another color. Hang on. Let's go to yellow. That should be easier to see. Along the bottom, yeah, it's a bit better. I have time. What happens is if I start with a high amount of a reactant, it drops. It drops quite quickly and then slows down. So that is the reactant. If I change my color now, if I can change my color, let's try changing color. Let's change it to blue. What is happening simultaneously is that, oh, that's a rubbish color to be in. Sorry, hang on. You can't really see that very well at all, can you? My apologies. Let's find a better color. Let's go white. So what I drew was, oh, sorry. What I drew was this. And this is the product, the amount of product. So that means that the definition of rate is the rate at which either the reactant decreases because it's decreasing, or the product increases. So it's the rate at which the concentration of the reactant decreases with time. Now, this is going to be measured in something like moles per cubic decimeter over seconds. In other words, moles per cubic decimeter per second. Okay, that's how we measure it. Now, we could have said it was the product here and its increases. It doesn't matter which one we use, they're both okay. All right, so it increases, the rate is going fast at the beginning, the steeper it is, the faster it is, and then later, as it slows down, it goes more horizontal. So you've got to know that the one which is increasing is the product, and the one which is decreasing is the reactant. Okay, here's another one. This is one looking at surface area. This is a really simple experiment. And in this, they have three tubes, and the three tubes have got identical amounts of the same acid in each. It's hydrochloric acid. And here we have on the left, we have some powdered calcium carbonate. Here we have some small pieces of calcium carbonate, and here we have some larger lumps, but they're all the same mass, okay? That makes it a fair test. So the person's going to just add them. Let's just see what happens. I think you know what will happen. Well, there's music going on. That's music because in my labs, I allow music. Now that second one is probably bubbling a bit faster, but the third one is bubbling much more. So you can see that the first one, which is the largest lumps, is going slower than the smaller lumps, which are going slower than the powder, which is really fast. Now I'm going to move this on, and we'll look towards the end. This one has finished. The powder has finished. This one is still going pretty fast, but still, and that one is got lots left at the bottom. And that's just showing that the smaller the particles, if you've got a solid, the faster the reaction goes. Now, the reason for that is really quite simple. Let's say we have a solid, and we have a solid, and it's in a lump like this. So these are particles of calcium carbonate, and the acid is going to attack it from the outside like this. To start with, these particles inside cannot react. Now, obviously, even very, very small pieces of solid contain powder which is trapped inside. This is just meant to be like a model to show it. So those ones there can't react at first. But if instead of this, I break it, and I break it into 4 pieces like this, and the acid is just the same as it was before, now the acid can get at all of the particles. In other words, breaking up a bigger lump into smaller lumps makes it possible for these ones which were stuck in the middle to react. In other words, when we crushing lumps makes more particles available. And this is the important thing for reaction, because otherwise they can be trapped inside. Okay, so they're not trapped anymore. That's simple. It's nice and easy. So the next one is about a catalyst. Can I get them to shut up? Hang on. Okay, this is a solution, and in this solution there is a chemical which can be decomposed by another chemical which is in here. And basically they will produce carbon dioxide. And when they produce carbon dioxide, it bubbles. But you will be able to see here that there are no bubbles to start with. So what has to happen first is it has to be heated up. When it is heated up to about 75 degrees, it starts to bubble, but it doesn't bubble very well. So what this is about a catalyst. And the catalyst is a pink liquid. And we're going to try to make them, these people, they shout a lot. This is a school in London. We're not going to listen to them because they shout such a lot. So let's move it on to the point where they are starting to heat it. So here it is now being heated and it is getting hotter, but it is not yet producing bubbles, okay? Not yet producing bubbles. Obviously, they like to dance as well as do the chemistry, which is not very useful. Anyway, so they're going to heat it up. When it gets to about 75 degrees, there are a few bubbles in there, which is why it's looking a little bit milky, but not very. When it gets to 75 degrees, they will pour in the pink liquid. Now, the pink liquid is called cobalt. There it is. The one showed you you see it. This one here shows you it just at the bottom of the screen. Then there it is. And then they're going to pour it into here and you will see what happens. They are seeing small bubbles, which is why it's looking a little bit milky, but they're very small bubbles. But it's just about 70 degrees, so 75 degrees. So they're going to pour in this pink liquid. What happens is that the pink liquid is a catalyst, and so it speeds up the reaction. It makes it go better, and you'll see what happens. Now, along with some catalysts, this one changes color, but it also changes back. So here we go. We're going to add the pink liquid, cobalt chloride. Going to add it to here. Come on, girls. Come on. They're going to turn the Bunsen off. Right. It goes in. Nothing much happens to start with. It's gone green. But now, remember I said it gives off carbon dioxide. There. That is producing a lot of carbon dioxide now. So the reaction is going much, much faster now. And it's gone green. And now it's going back to pink, which shows it has turned back into the original chemical. Now that's really important. Let's just see that bit again. About here. As it goes in, it turns color, but at the end it turns back to pink. Now that's really important because that shows that the catalyst is unchanged at the end. That is really important. Catalysts speed up reactions. There it is going much, much faster. Much faster, and then it's gone back to pink, which means it has returned to its original state. Now, what is happening here is that the catalyst, many of you will know this, but in the little video with the American woman, we saw this graph. This is energy up the side. This is time. Well, it's actually progress of reaction, but it doesn't matter. This is the reactants here. And this is the products down here. And if you remember, the difference between here and the top was called the energy of activation, which is often given that symbol, energy of activation, EACT. I'm going to try and change the color. Now, when you have a catalyst, what happens is it does this. In other words, it's got a lower E act. That means that at the same temperature, it can go faster. I'm sorry if that's not very visible on your screen. It's not very visible on mine. I'll try and change color again. That means sorry, let me just, come on. Okay, so it goes here, it's lower. Okay, it's a lower bump. And that means with the catalyst, it's got a lower energy of activation. Now that's really important. That means at the same temperature, it can go faster. So faster rate at the same temperature. So they didn't heat it anymore. It just went faster. Okay. So then you need to know about the factors affecting the rate. And you should know its concentration, pressure, which is only for gases, temperature, surface area, light, which is only a few reactions, and catalysts. So what I'm going to do is I'm going to look at each one of those in turn. I won't take very long at all. I'll go very fast through these, and I'm going to do it via a table which shows you what is happening. So it might be worth you writing a table out, which has got the factor, the effect on the rate, and then collision, frequency, energy, and orientation, because that is what that's how we're going to explain each one of them. Now, obviously, if I get concentration increase, the particles will be closer together. If the particles are closer together, they will collide more. I can show you that in a different way. Let me just show you something slightly different. Okay, this is meant to be red particles and blue particles, which will collide to make yellow and green ones. Let me see with them happening. There they are, crashing into each other and changing. Now, when the concentration is low, this last red one may take some time before it hits a blue one. Oh, yeah, finished. Okay. But now if I restart it, but now I have many more blue ones, higher concentration of blue ones, obviously it should happen faster because now they're all going to move around and now there are more blue ones for them to hit. So here we go. Oh, they're starting to react. Oh, finished. Okay. So high concentration, let's just restart that. Here it is again. Lots more blue ones, and therefore it's much quicker for, even though this is pretty random, so there's a red which is still escaping. Oh, there it is. Whereas when we have a low concentration, it's much more difficult. Okay. The second thing which is also true, which I'm just going to do very quickly now, is to show you what happens if I drop the temperature. So the temperature is over here on the left-hand side. I'm going to lower the temperature and you'll see what happens. Now the same particles, but now they're colder. Now I get them to try and react, and they're just going much more slowly. So not only will they not crash into each other so often, but when they do, it will be much more gently. Okay, this is going to take, oh, look, oh, yes. So they're going to crash into each other. This is going to take ages. This is going to take ages. Let's heat it up. And you see them going faster. Now they're going much faster. And now, although this red at the bottom is still escaping, oh, there we are. It's over. Okay, so heating up makes them go faster and will make them collide more. Okay, so let's go back to our other picture. Okay, so when I increase the concentration, the effect on the rate is to increase it. And the only thing it affects is collision frequency. It increases collision frequency. In other words, they collide more often. Do they collide harder? No. Does it change their orientation? In other words, how they hit each other? No. It just increases how often they hit. The same is going to be true of pressure. Pressure is only true for gases, okay? Only true for gases. But when you increase the pressure of a gas, the rate increases. And that's because you're pushing them closer together. That's like concentration, and therefore they collide more often. Next is temperature. Now, temperature speeds them up, as we just saw. We've nearly finished. We've nearly finished, guys. Patience just for a minute. It affects rate by heating things up affects a rate. So if you want to cook something and you want to heat it up a lot, it will cook faster. You may burn it, but it will react faster. Because they are moving faster, they collide more frequently, more often, but they also collide harder. And that means that the increasing temperature is giving them the activation energy. Okay, it's giving them the activation energy. That's very important, that it is not just colliding harder, it is supplying them with the activation energy. The next one is surface area. We saw the surface area. If you crush things, so you increase the surface area, it increases the rate. And that's just because more of the particles can react. Light only affects some reactions, only a very few reactions. It's some reactions. But what it is doing, it's supplying them with energy, not necessarily so they can move faster, but so they have more energy. They are already starting to react. And the last one is a catalyst. And the catalyst increases the rate of reaction. It may increase collision theory by concentrating the particles on its surface, but it increases the effectiveness. By lowering the activation energy, it makes it easier, and it sometimes helps orientation. So overall, this is the table, okay? And we're going to stop here in just a minute. I'm going to show you what your teachers will get, and that's a set of questions. I will come back to this. There's a set of questions which are all about reaction rates, okay? And it's all about this. Okay, this is the table which is most important, but you need to understand and sort of understand what is happening in terms of them colliding, crashing into each other with frequency and with more force. That is most of the changes. Okay, you've been very patient and I appreciate it very much. So we're going to stop sharing now. Oops. Stop the sharing. I'm going to say that's the end of the lesson, so I'm going to stop recording.